Welcome to Matematika. Today we're going to do some problems and solutions of 1.8 rational functions and zeros. But before doing that, let's review some terms, definition of terms that are related to rational functions and in getting zeros. We'll do the first term, a vertical asymptote. We have been talking this vertical and horizontal asymptote for several videos, but we have to get more to know more of these terms. So a vertical asymptote of a rational function is a vertical line that the function approaches as y goes to the positive or negative infinity. Well, the horizontal asymptote is a horizontal line that the function approaches x goes to the positive or negative infinity. Whole or holes, it's many, is a point in which the function does not exist. A point on the graph where the function is not defined. And it occurs when the factor in the numerator cancels out with the factor in the denominator, creating a removable discontinuity at that point. All right. So let's practice. Let's look at the graph and find the equation of the horizontal and vertical asymptote. Okay. So I'll start with this graph right here. When I say, I'll start with vertical asymptote. Okay, vertical. All right. I could find somewhere here. This is 0 right here. So this will be 1, 2, 3, 4, 5. All right. I can have a vertical asymptote right here. This line. All right. So where is it located and where did it hit on the x-axis? So let's say it hit at 1. All right. So the vertical asymptote is x equals 1. Well, the y asymptote, as what does the definition means? All right. For the vertical asymptote, I'll start with vertical. It says as y goes to positive or negative infinity. Right. As y goes to the negative infinity right here and the positive infinity right there. For the horizontal asymptote, okay, it's a line, right? It's a line of a rational function that approaches as x goes to the positive or negative infinity. So where is the negative infinity? Right here. This is going to the negative infinity and this x goes to the positive infinity. So where can we draw our asymptote? Horizontal asymptote. Right here. It never intersect the curve, but it's just touch, like pass through until it, as we go on and on and on, it will until it reaches to 0. So at what point our horizontal asymptote be? At y equals negative 4, right here. All right. Let's do this. I like to use another color for this. Okay, let's choose another color. All right. Since the curve are blue. So I'll start, might as well, I will just do VA for vertical asymptote and HA for horizontal asymptote. Okay. Do we have a vertical asymptote here? As right here. So this is 1, 2, 3. When x is equals to 3, we were able to have a vertical asymptote as x goes to positive infinity and it goes down to a negative infinity. All right. How about the horizontal? This is our horizontal, right? As x goes to positive infinity right here and negative infinity. Okay, so y is equals to 0. Okay, let's do this. Vertical asymptote. Okay, we can have this vertical asymptote right here. So when x is 0. For horizontal asymptote, okay, we can find the horizontal asymptote as it touch the curve but never intersect the curve. This line. This is for negative infinity and positive infinity right there. So when y equals 6, all right, how about number 4? So vertical asymptote, horizontal asymptote. You know, some line that touch the curve, okay? So x, as y approaches positive infinity and negative infinity. So the x there is 3. That's for vertical. And for horizontal, of course, we have this, we have no other line. We cannot make another line for horizontal asymptote at y equals 0 as x approaches to positive infinity and negative infinity. All right. All right. Let's have this graph. Vertical asymptote and horizontal. So we have a vertical asymptote here. Touch the curve but not intersecting the curve. As y approaches positive infinity and negative infinity, the x is equals to 0. Okay. Do we have asymptote y asymptotes here? Okay, this one. This one right here. As x approaches positive and negative infinity, until it get, as we go on and on and on, until it get into equals to 0. So therefore y is equals to negative 4, somewhere here. Okay, let's do this graph. All right, let's do the vertical asymptote first. Touch the curve Okay, right here. So it passes at 1, 2. This is negative 2. So x is negative 2 as y goes to positive infinity and negative infinity right here. Horizontal asymptote y. Okay, I found one that touch the curve but never intersect the curve. Just touch the curve. As it goes to positive or negative infinity. So the horizontal asymptote is when y is equals to 4. That's it. It's just look at the graph and you know where your horizontal and vertical asymptote is located. Use the rational function to answer the following. We have an x plus 2, function of x plus 2 in over 3x squared plus 6x. Now, the first thing that we have to do is to find out. We can equate our numerator to 0 to find the zeros, and the denominator 0 to find the vertical asymptote also, and to find out the y-intercept. All right. You're asked the domain. Okay, what we can see here, if let's try looking at this. X plus 2 is already a factored form, but in the denominator, we come out a common factor of x, 3x, 3 and 6, so common is 3. I like to use the blue one again. So 3 and x. What is left is x plus 2. Oops. I can see that if this can be cancelled. We found some holes here. All right. We can see 3. You can see a negative 2 and 2, 0. Okay. So what will be the domain? We can have negative infinity to negative 2. Union with negative 2, 0. Union with 0 and positive infinity. What is our whole here? When x plus 2, that means x is equals to negative 2. When we equate this to 0, and the denominator, remember in rational function, the denominator should not be equals to 0. All right. So what are our zeros there? 3x is equals to 0. That means it's what? Nothing. You have no zeros. None. Vertical asymptote. Okay. 3x equals 0. That means x is 0. Horizontal asymptote. Let's look at the degree of the numerator to the first, and the degree of denominator is to the second. So that means the m is less than n. What happened to that? Our horizontal asymptote is 0. Remember the degree. M is less than numerator, degree is less than the denominator. And where is the y-intercept? Y-intercept, when we replace 0 to the equation. Okay, so for example, this is 0 plus 2, and then 3 times 0 squared plus 6 times 0. So this is 0, that's 0, that's 2. 2 over 0, anything that is divided by 0, so our y-intercept does not exist. Nothing. You cannot find, does not exist. Okay. T to the third minus 2t squared over t squared plus 3t minus 18. So we need to factor out the numerator. We have t squared, t minus 2. We factor out the denominator. So t, factor of 18, and our middle is positive. So this will be 6 and 3. Denominator not equal to 0 for rational function. And for zeros, we can equate the numerator to 0. Do we see any holes here? Nothing. We don't have anything to cancel out. So our holes is 0. So what we have is t equals negative 6 and 3 for vertical asymptote when we equate that to 0. So t, or we could say x, is negative 6 and x is 3 from here. For zeros, t squared equals 0 and t equals, okay, right here, t squared equals 0. So that's a square root of 0 is 0. T minus 2 equals 0. So t is equals to 2. That means your zeros are x equals 0 and x equals 2. What else do we need? Horizontal asymptote. Let's look at the degree of our right here. M is greater than n. That means the numerator, the degree of the numerator is greater than the degree of the denominator. That means, remember, you have no horizontal asymptote. Remember the case 1, case 2, case 3 that we have. Okay. The y-intercept. So if we are, we didn't do the domain. Okay, can I erase this? So the domain would be, we have a negative 6, we have a 3. So it will be, if we look at this is 0, this is 3 right here. Then we have a negative 6. So this will be negative infinity and positive infinity. So our domain would be negative infinity to negative 6 union with or and this interval right here, and negative 6, 3, and 3 union with 3 and positive infinity. So the y-intercept, when you replace a 0 in your function, so if I say t cubed, that is 0 cubed minus 2 times 0 squared over t squared, 0 squared, plus 3 times 0 minus 18. So this will be cancel. We have a 0 over negative 18, which is a 0. That means that is our y-intercept is 0. Okay, I think we answered everything. If you will be asked question like this, use the graph created in a sine table. So we did a lot of intervals using sine. Let's use this. Okay, I will extend the graph so that we can find what happened between interval of negative infinity to negative 5. Negative 5 is right here. So negative 5 is a vertical asymptote where the vertical asymptote is located. So this is negative infinity. Then we have a negative 5. Then negative 5 to 2 here is a 0. Then negative 2 to 2. So 2 is another vertical asymptote. And 2 to the positive infinity. So if we look at the interval of negative infinity to negative 5, both ends are towards the negative of the graph. That means this sign is negative. Okay. Negative 5, since negative 5 is a vertical asymptote, that means it does not exist. Okay. Remember in our definition, that point does not exist. What else do we have as a vertical asymptote? 2. Okay. So does not exist. Negative 2 is a 0 right here. So this is a 0 for negative 2. How about negative interval negative 5 between negative 5, even negative 5 to negative 2? This interval right here, if you try to look at, all are up. So these are positive. All right. From negative 2 to 2, this interval right here, you see the graph started to move down. That means this is negative. Right? 2 to infinity, we have a positive. Going to the positive infinity. So it's positive. It's above. The curve is above. So it's positive. All right? I think that's it. We complete the table. The function of f is given. Okay? Given by f of x equals x squared plus 2x minus 24 over 4 minus x. Which of the following describes the function of f? Okay, let's look at this. We're going to factor out the numerator. So negative 24 is 6 and 4. So the middle is positive, so we have plus 6 and minus 4. And we have to equate the numerator to find the zeros. We have x minus 4, 4 minus x. So how can we change this into, we multiply with a negative 1 to make your x into a positive and 4 to be in a negative. Okay, so that we can cancel, we can find a holes here if there is a question about hole. And our 0 is this, x plus 6 equals 0, so x is negative 6. We have, this is the 0 from our numerator. Okay, so let's start. The graph of f has an x-intercept at x negative 6. Okay, and a vertical asymptote of x equals 4. It's not x equals 4 on the vertical asymptote, right? So this is not the answer. The graph of x has an x-intercept at negative 6, correct? And a hole at x equals 4. Yes. This is our hole. X minus 4. So x is 4 is the hole. The hole. This is a hole also. So this is correct. Is there another one? X-intercept at negative 6. Vertical asymptote at negative 4. No. The graph has an x-intercept and a hole at x equals 4. No. The graph has an x-intercept and x equals 4. No. So our answer is number 2. Use the table. Okay, we have a sign table here. Which of the following must be true in the function? The graph has a maximum and minimum at 2. Wait a minute. We'll have to identify. This one right here is a 0. This is undefined. And we have another 0 right here. So we have an undefined. Okay. So when it's undefined, it might be a hole or a vertical asymptote. All right. This is a 0. The graph has a maximum equals to negative 3 and a minimum of 2. No, it's not. The graph has minimum at negative 3 and a maximum at 2. No, it's not. F has exactly 2 distinct real zeros. So how many zeros do we have? 1 and 2. Okay, this is correct. F has exactly 3. No, it's not 3. No, it's not. The other one is undefined. The graph has a vertical asymptote at x equals 0. No. All right, so our answer here is at C. Which of the following could express for the function of x? Okay, let's look at this one right here. If we equate this to 0, we have a hole there. We can cancel that out. So the numerator x plus 3 equals 0. X is equals to 3, x minus 2. So x is equals to 2. I'm just doing this to, find later on what the graph. So let's look at the zeros here. X, what zeros do we have? Negative 3. This is negative 3 and 2. All right, we have it. We have the 0 at negative 3 and at 2. So this answers our question. Because if you do this, the x minus 3 is 0, x is 3, which is not the 0. Then x plus 2 equals 0, then x is negative 2, which is not a 0. So that's not same thing with here. This is the tells us about the vertical asymptote or a hole, and it's not with x plus 3 and x minus 2. The more that it's in the denominator for 3 and 4 as well as 5. We found our answer in number 1. Okay, so I think we talk about a lot in our problems and solutions regarding the rational functions, zeros. We reviewed about the horizontal and vertical asymptotes and holes. Hole as the one we had in our algebra 2. Okay, so all I can say is that if I can do it, so can you. So don't forget to hit the like button and subscribe. See you in my next video.